Assalamualaikum warahmatullahi wabarakatuh. My name is Ahmad Fauzan bin Yatin. Metric number is 2020498826. Today, I will present about the topic of nuclear magnetic resonance spectroscopy. What is the meaning of spectroscopy? Spectroscopy is the study of absorption and emission of light and other radiation by matter, as related to the dependence of this process on the wavelength of the radiation. Now, we have know what is the meaning of spectroscopy. So, NMR spectroscopy is a technique that uses magnetic field and electromagnetic frequencies to study molecular structure at the atomic level of the sample, such as a small molecule like drugs and metabolites. NMR spectroscopy has become one of the most frequently used analytical tools to elucidate the chemical structure. It is particularly useful for carbon-based chemical compounds, also known as organic compounds. Samples are inserted in the center of the magnet and are positioned in the NMR probe, so the sample is located at the position of the strongest field and highest homogeneity of the magnet. The NMR probe consists of coils that are used to excite the sample and record signal responses at radio frequency. The basis of NMR is that nuclei behave like microscopic magnets. In a magnetic field, they spin around the main magnetic field just like a spinning top. This motion is called the precession. Different nuclei have a different spins, so the one spin with one half can exist in one of two possible spin states. These include the following atomic isotopes. The hydrogen nucleus, usually referred to as simply the proton. It is present in almost all organic compounds and is the one most frequently analyzed by the NMR. The precession frequency is given by the following equation and is dependent on the strength of the magnetic field and also the gyromagnetic ratio with which a constant for a given isotope. The frequency of the precession is proportional to magnetic field strength. Now, what are the criteria required for the NMR signal? Just we have seen that nucleus should have a spin quantum number I is equal to half. Nuclei which have half spin quantum number are the nuclei which are having either odd number of protons and even number of neutrons, or even number of protons and odd number of neutrons. So, only these nuclei can give that NMR signal. We should apply external magnetic field, and under the influence only the nuclei can have the two spin states. We have to supply the sufficient energy in the form of electromagnetic radiation that resonates with the energy gap for most of the nucleus. The energy gap resonates with the radio waves, so we can supply the wave as the electromagnetic radiation in order to observe the NMR signal. Additional local field differences are introduced by changing electron densities in a molecule. A higher electron density results in more shielding and thus a lower local field and lower spinning frequency. A proton with a high electron density around it experiences a lower magnetic field and therefore a lower Lyman frequency. And a proton in an electron-poor environment has a higher frequency. Typically, protons in an electron-rich environment are referred to as shielded, and those in an electron-poor environment are referred to as de-shielded. Now, if we pass this with an radio frequency pass, we will get two signals in our free induction decay or FID. One will oscillating at high frequency and one will oscillating at a low frequency. The FID is a representation of the wave in the time domain. The Fourier transformation mathematically converts this to the frequency domain, which allows us for a visual representation in a NMR spectrum. The different frequency we call the chemical shift, and they depends on the chemical structure of the nuclei, with the shielded protons giving peaks at the right side and the de-shielded protons giving peaks on the left side. Spin-spin coupling is another characteristic of NMR that is useful in determining chemical structure. The chemical shift of a proton will be affected by its neighboring proton. Let's say we have a proton A with proton B in close proximity. In a magnetic field, proton B will either be aligned with or against the magnetic field. thus slightly perturbing the field that proton A fills. Proton A will be split into a doublet. If there are two protons close by, the peak will be a triplet. Three neighboring protons will be a quartet. For splitting to occur, proton B must be non-equivalent. That is, it has to be in different chemical environment. Let's take a look at a couple examples. The proton Hs farthest from the chlorine will be affected by the single proton Ha, and the peak, centered at 2.1 ppm, will be split into a doublet. Ha has three neighboring protons, and its peak, centered at 5.9 ppm, will be split into a quartet. Note that the proton Hs are equivalent, so they are in the same chemical environment and they do not split each other. Here we have methyl propionate with three groups of protons. For protons to couple, they have to be within three bonds of each other. The proton Hx on methyl group are too far away to be affected by other proton in the molecule, and they will show up as a singlet. But the Ha protons are within three bonds of proton Hb, and the peak will be a quartet. The proton Hb will be affected proton Ha and will be split into a triplet. Keep in mind that if the neighboring proton is in the same chemical environment, for example a symmetrical molecule, then there will be no spin-spin coupling. So 1,2-dichloroethane is a singlet at 3.75 ppm, and there is no splitting observed. When two protons on neighboring carbon atoms split each other, this is called vicinal coupling. Under certain circumstances, we can have two protons bonded to the same carbon atom split each other. This is called chemical coupling. Just as with a vicinal coupling, geminal coupling only occurs if the two protons Ha and Hb are in different chemical environment.